So the next few examples are just practicing using this identification of the highest degree when we are looking at these rational functions, these fractions. So notice how we do have a limit at infinity, so we are going forever to the right on this graph, and we do have it available. So notice how if we anticipate what our answer should be, the further we go to the right, looks like we level off at a y value of 0. So we should anticipate a value of 0. Let's see if we can use those three rules appropriately. So looking at the equation, notice how the degree of the top is 1, the degree of the bottom is 2. So we have a slow growing function over a fast one. In other words, we have a small number over a big number. So if you make the small number really small and the big number really big, because notice how we're going towards infinity, this would ultimately result in getting closer and closer to 0. So this limit value would be 0, and this is signifying that we have a horizontal asymptote to the right, because according to the limit, the x's was approaching infinity, meaning to the right-hand side. The next one is we are also approaching to the right, so graphically, since we have the picture, notice how we approach a y value of 2. So let's see how we can get that from the function. The degree of the top is 2, the degree of the bottom is 2. The other values are insignificant because these are the highest ones. These are the most effective or affecting terms of the top and the bottom, so the other ones don't really mean much. So if the degrees are the same, notice how we would essentially be left with 2x squared over x squared. Those would cancel, and we're left with 2 over 1, signifying that we have a horizontal asymptote at 2 to the right. Looking at the third one, again, if we approach infinity, this is a good example of a slant asymptote, how it's not completely horizontal, okay, it's more angled. So notice how as we go forever to the right, it looks like the graph would be going up forever. Let's see if we can get that same result here. So the top degree is an x squared, the bottom degree is just an x. The other terms are insignificant because these are, in a way, the most powerful ones. They're the largest degree. So if we have a fast growing function over a slow growing function, we're going to have something huge over something small, and if you were to divide a very large number by a very small number, you'd get a very, very large number. So notice how we'd be going towards infinity. So this is signifying that we do not have a horizontal asymptote to the right, rather the graph goes up to the right. All right, I don't think those are too bad. We do have 2 more to check out on the next page, though, on 73. So for these two, we're going to take a look at if we were to approach negative infinity. This just means we're going to the left on the graph. So on the left-hand side of our first one, notice how we approach the y value of 2. Let's see if we can get the same result. So if we take a look at the function, we have a highest degree of 2 on the top and the highest degree of 2 on the bottom. The other terms are insignificant. X squared divided by x squared would essentially cancel, and we're left with 2 over 1, which is 2. So we have a horizontal asymptote at 2, at the y value of 2, to the left in this case, because we were approaching negative infinity. For the next one on the slant asymptote, notice how as we go toward the left, we happen to go down. So let's see if we can get that result from the equation. The top degree is a 2, the bottom degree is a 1. The other terms are insignificant. So we have something fast divided by something slow. So a very, very large number divided by a smaller number would get very, very large. The depending factor here is, does it get very, very large positively or very, very large negatively? So that's where we have to kind of analyze, since we are approaching negative infinity, what would happen. And notice how if you thought about plugging in negative infinity into the x squared and the x, a negative infinity squared would be a positive result, whereas this would stay a negative result. So positive divided by negative would ultimately be a negative. So notice how we would be going down towards negative infinity. So there's no horizontal asymptote, rather the graph goes down to the left. So these three rules, I don't think they're too bad. We just have to kind of keep them straight, whether we have a top degree that's bigger, a bottom degree that's bigger, whether the degrees are the same. Okay, we just have to make that distinction between the three of them. So graphically, a limit at infinity can yield a horizontal asymptote. Okay, not always, because notice how the first one up here did have one, whereas the second one did not. So it can give the location of a horizontal asymptote. And in pre-calculus, just like we discussed today, we can analyze those growth rates, meaning is the top growing faster or is the bottom growing faster. So we can compare the growth rates of the top versus bottom. Now, this is all well and good, but in terms of our justification, we can no longer say that we have a horizontal asymptote because the top degree is bigger than the bottom or vice versa. Okay, so this is no longer a viable justification for the reason that we have a horizontal asymptote. In order to justify the existence of a horizontal asymptote, we will have to use a limit. So you can use the rules to identify whether a horizontal asymptote is there, but if a question asks you to justify it, you must write a limit statement. So we can only say that we have a y value of c is a horizontal asymptote only if we have a limit approaching either positive or negative infinity that results in this value of c. So very similarly to how you need to write a limit statement to justify a vertical asymptote, you must also write a limit statement to justify a horizontal asymptote.